Hello and welcome to Empowered Learning. Welcome to the second part of the video series on solving systems of linear equations. And so in this example, we are going to solve systems of linear equations via substitution. So our main objective here, whenever we do substitution, is to write one equation in such a way to where we have it as one variable in terms of another. So in this case, we're going to choose to write y in terms of x. After that, then we want to substitute the variable that's solved for into the other equation that we didn't use for the unknown variable, to solve for the unknown variable rather. So from that point, we'll find out what the first unknown variable is and use that answer to be able to find out what the other unknown variable is. If we're able to do so. So in this example, we see we have two lines, 2x minus y equals 5 and 5x plus 2y equals 8. And we essentially want to figure out where do these two lines cross. So the first thing that we do using the substitution method is that we write y in terms of x. And so we do that by starting off and realizing that if we have our equation here, we can subtract both sides by 2x. So when we do that, we end up with a negative y equals 5 minus 2x. From that point, we need to solve for positive y, not negative y. So we multiply both sides by negative 1. And hence, we end up with 2x minus 5. We take 2x minus 5, and then we substitute that into the y here. And once we do that, this is what that ends up looking like. So we have 5x plus 2 times 2x minus 5 equals 8. We distribute our 2 across. And then from that point, we say 5x plus 4x minus 10 equals 8. Combine like terms here. And so we see that when we combine like terms, we will get 5x plus 4x is equal to 9x minus 10. We'll add 10 to both sides here. And in doing that, that's how we will get 18. And then from there, we know that dividing both sides by 9 will yield us x is equal to 2. So from that point, we know that the x coordinate for where both of these lines cross will be at x equals 2. To find the corresponding y value, we go back up and choose one of our two original equations. In this example, we are choosing to use equation 1 again. So when we do that, we take our equation 1, which we see here, and we substitute in 2 in for x. Substitute in 2 in for x, and this is what we come out with here. Okay. So once we do that, we see that 2 times 2 is 4, and then if we solve for y, we see that y ends up being a negative 1. So that will be our y coordinate for the point where these two lines cross. And so again, just to kind of give you a visual, we have one line that has a negative slope, one line that has a positive slope, and we know that where these two lines cross will be at the point 2, negative 1 on a graph. So from there, we're going to go ahead and move to another example. Well, not another example, the same example, but doing it via the elimination method. So in the elimination method, the thing that is different about it is that we start off trying to figure out what variable we want to eliminate, but we do it by using 3 rules. These rules are called elementary row operations or elementary row rules, and so I'm going to go through those 3 rules as I show you how to solve the problem, and then after that we'll display it in another example. So the 3 rules are as follows. First rule, we can interchange the order of any equation in our system. Okay, so we currently have this as equation 1, 2x minus y equals 5, and we have 5x plus 2y equals 8 as equation 2. If we wanted to switch those around, we could, and that would not change the integrity of the system. So if we switch them around, our system would now look like this, and there would be no problem with that. Okay? The second rule says that we can take any equation and multiply both sides of any equation by a non-zero constant. And so here, if I just use this example that I have here, let's say I wanted to multiply both sides of equation 1 by 2. Well, if I did that, then the top equation that you see here in this second system is exactly what I would get. And that equation would be equivalent to the first one that we had. Okay. The third rule that we have is that we can replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation in the system. So basically what we're saying is to use this example, this is a non-zero multiple of an original equation we had, and we can add that to one of the other equations that we originally had in the system. Okay? The result that we get from that could also be a new equation that could be a part of the system. Of course, here we see that when we add the y's, the terms with y will go to 0. And of course, here we just have 9x there. That will go to 0, and that would be 18. And that's exactly what we see down here. Okay? And so now we can, instead of having 2x minus y equals 5 and 5x plus 2y equals 8, now we can have a system that just has 4x minus 2y equals 10 and 9x equals 18, and those will be equivalent systems. Okay? Now note here that whenever we added our two equations at this point here, that this was a non-zero multiple, but also we see that our terms with y were eliminated when we did that. And so that is essentially what elimination method or the addition method is all about. Trying to inspect your system to see, hey, if I want to eliminate this variable, what would make that happen? In this particular case, if we look back at our original system, you'll see that if we wanted to eliminate our variable y, that in order to have that, we needed to have a 2 right there, so that thus we would have a negative 2y here. Now, of course, we just can't stick a 2 there to make that second term negative 2y. So what we would have to do is multiply our whole entire equation here by 2 to make that happen. Hence why we went ahead and did that in rule number 2 here, okay, as an example of rule number 2. So now that we kind of understand what's going on here, if we put everything together, we'll see that we start off with these two equations. We multiply the first equation by 2, and we get this. And then we notice that if we were to add these two systems together, that will cancel. That will give us 9x equals 18. And of course here, I just have it as 0y to show you that it eliminates. And then thus, from here, we see that 9x is equal to 18. And from that, we solve for x, and x is equal to 2. So from that point, we can either now use equation 1 or equation 2 to plug into to plug x into so that we can find out y. So in this case, I'm going to use equation 2 to do that. And our equation 2 was originally 5x plus 2y equals 8. So I'm basically taking x equals 2 and plugging it in there. And that is what we see right there. So when we do that, we see that that ends up being 10 plus 2y is equal to 8. And of course, if we solve this linear equation for y, we see that y ends up being a -1. And thus, again, we see that the two lines both intersect at the point 2, -1. And so to reiterate the vocabulary that we saw in the first video, we know that since we have one solution, the equations were independent. This system is consistent because it has at least one solution. Okay, so it's independent, the equations are independent, and the system itself is consistent. This particular example is just here just the test to make sure that you understand the relationships in between the slopes and y-intercepts of lines and how that tells you if you had two lines that you're trying to see where they crossed, whether you would have a solution or not, and if so, whether you would have one solution, infinitely many solutions, or no solution. So we see that we have a system here where y is equal to mx plus b and y is equal to nx plus c, where m and n are the slopes of the respective lines and b and c are the y-intercepts. If we look here, our first question says, if the system has a unique solution, meaning that we have distinct values for x and y, what is the relationship in between m, b, n, and c? Well, we start off by knowing that if this system has a unique solution, then we know that the lines cross at exactly one point. So we're going to have lines that look like this. Knowing that, the one thing that we know is that the slope of the first line and the slope of the second line have to be different. So we know that m will not be equal to n. Now, as far as the relationship in between b and c, there is no real relationship, because we could either have a case where b is equal to c, meaning that the y-intercepts are the same, or we could have a case where the y-intercepts are different. And so this is what I'm actually trying to communicate down here, is that the only real relationship, if we know that the system has a unique solution, meaning one point where both lines cross, is that the slopes have to be different. And in this case, that means m is not equal to n. For the next question, it says, what if the system has infinitely many solutions? Well, if the system has infinitely many solutions, we know that that's a case where the lines are essentially the same. Okay, so we may have one line that looks like this and another line kind of going through it like that, that is essentially the same. So in that case, we know that the slopes of both lines and the y-intercept of both lines have to be the same, because if a line is similar to another one, its slopes and y-intercepts are the same. So that's what I'm saying here. For the next question, we'll see, all right, well, what if the system has no solution? Well, we know if it has no solution, then the lines are parallel to one another. And what that basically tells us is that the slopes are the same, but the y-intercepts are different. Okay, so in that sense, we see what I'm saying here. These are the slopes, and here are the y-intercepts. Y-intercepts are different, but the slopes are the same. All right, so now we're going to work through a few examples here. And so we'll start with this first one. We want to solve this particular system. And so to do that, first thing that we'll do is notice that we already have y written in terms of x here, so that kind of makes this easy to do. So all we need to do is take this 5 halves x and stuff it in for y there. So if we do that, we'll just have x plus 3 times 5 over 2x is equal to 3. And then from that point, we just need to find out what x is. So noting that 3 is the same as 3 over 1, we multiply and we have 15 over 2x is equal to 3. And so here, to get rid of the fraction, we can multiply both sides by 2, because 2 is the only denominator for the fractions that we have. So distributing, we would have 2x plus 2 times 15 is 30, and 30 divided by 2 is 15x. And then here, 2 times 3 is 6. From there, we combine like terms, get 17x is equal to 6, and then we divide both sides by 17. And we see that the x-coordinate for where these two lines cross will be at 6/17. So now that we have that done, we can now take our value for x and use this equation again to solve for y. So y is going to be 5 over 2 times x, and x in this case is 6/17. So we come here, we see that 6 and 2 have a common factor of 2. So 2 goes into 2 once. Having some technical difficulties here. See if I can fix that. Just trying to move this back down. Okay, not sure what's going on here. Okay, so here we see that again, that 2 and 6 have a common factor of 2. So we know that 2 goes into 2 once, and 2 will go into 6 3 times. So from there, 5 times 3 is 15, and 1 times 17 is 17. So y will be 15/17. So from here, we see that the point where these two lines will cross each other is at the point 6/17, 15/17. Okay, so this is the x-coordinate, that's the y-coordinate. So we'll go ahead and move on to the next example. For this one, we're going to do this by substitution again. So we're going to write, in this case, we're going to take y, well, let's see, I think it would be better to do x in terms of y here. Okay, so if we do that, then we will take the first equation, 2x minus 4y equals 0. If we add 4y to both sides, we'll see that 2x is equal to 4y. And if we divide both sides by 2, we'll see that x just ends up being 2y. So we take that and plug it into x here. We'll see that this will be 6 times 2y plus 8y is equal to 5. And then from that point, 6 times 2 is 12, plus 8y equals 5. 12y plus 8y is equal to 20y. And now to solve for y by itself, we just divide both sides by 20. These 20's reduced to 1, and we see that 5 over 20 is the same thing as 1 over 4, because 5 goes into 5 once, and 5 goes into 20 4 times. So now from there, we know that our y-coordinate is going to be 1/4. Now we need to find our x-coordinate. So we can do that by going back to one of our original equations here. I'm going to take the first one. So we can say 2, let's see, get rid of that. So we're going to say 2, still having some technical difficulties here, okay? So 2x minus 4y is equal to 0. And now we're just going to let y equal 1/4. And so 4 times 1/4 is just 1. We add 1 to both sides. That, of course, the 1's eliminate to 0 or cancel to 0. And then the last thing we do here is divide both sides by 2. When we do that, x ends up being 1/2. So the point on the graph where both of these lines cross would be the point 1/2, 1/4. Okay. Moving on to the next example, we see here that we have y already written in terms of x, so I'm just going to take this and stuff it in for y right there. So if we do that, we have 3x minus 3 times x minus 4, all that equals 12. If we go ahead and distribute the 3 to both terms there, you'll see that we have 3x minus 12 equals 12. And now if we distribute that negative, we'll have 3x minus 3x plus 12 equals 12. And from here we know that 3x minus 3x just cancels to 0, and we have 12 is equal to 12. In this situation, since we have two numbers that equal the same thing there, this is telling us that no matter what we choose for x and y, the points are always going to be on both lines. So this is a case where we have infinitely many solutions. Okay, and so if you remember, for infinitely many solutions, we knew that there was at least 2 equations that were similar or that were identical. If I'm going to come up here and show you that these 2 lines are essentially the same line by going ahead and rearranging this top equation. So here, if you notice, we take this and kind of like how we did down here in this area, we multiply the 3 across both terms. You see we have y is equal to 3x minus 12. Okay, so if we rewrite that, and now if we were to subtract y from both sides and add 12 to both sides, do some separation here, then those 12s would cancel and we would have 3x minus y, those y's would cancel, and we would just have 12. And so you see that this line is the same exact thing as this line there. So another way that you could figure this out is if you can see, hey, can I write the lines in such a way to where they're similar to one another? If you see that you can do that, then you know you have infinite many solutions. If you see that you can't, then you know that either your lines are parallel or they do not have the same slope, and you end up having exactly one point where they intersect. All right, so this concludes the second part of the Systems of Equation video. I'll continue with the third part with more examples.